Hello, calculus students. This lesson is on local linearization. Now, a tangent line can be used to approximate the values of a function near the point of tangency. Here we have some sort of function. We'll call it f of x. Here we have a point of tangency at x equals a. So the coordinates of this point would be a, comma f of a. Here's our tangent line at that point. The equation of this tangent line would be y minus f of a. That's the y coordinate of the point that the line is passing through, equals the slope of this line, which would be f prime of a. You find the derivative of f and plug in a, you get the slope of this tangent line, and then times x minus a. If you solve this equation for y, you would just need to add f of a to the other side. So y would be f prime of a times x minus a, and then add f of a to that. Now this tangent line to the function at x equals a is sometimes called the local linearization of the function f of x at x equals a. It's a linear function that most approximates the function f near x equals a. Of course, as you go further away from a, such as over here, we can see that the tangent line and the curve aren't necessarily similar to each other any longer. And using function notation for this line, we would call it L of x, and then our linear equation. We'll use capital L to stand for local linearization. But it's nothing more than the equation of the tangent line at x equals a. Now, at x equals a, the function and the tangent line have the same output. But the further you get from a, you can see a potentially widening gap between the tangent line and the function. Now, if you go to the right from x equals a, some value we'll call delta x. This will take you to a new x coordinate. We'll call it b, and it's found by doing a plus this delta x. Now, at b, we can clearly see that the function and the tangent line would produce two different outputs. The function's output being here, and the tangent line's output being a little higher in this drawing. Now, as long as you don't go too far away from the point of tangency, these 2 points will be pretty close to each other. So you could use the output of the tangent line as a way to approximate the output of the function. Now, the slope of this tangent line is calculated by doing the derivative of the function and evaluating at a. Another notation for a slope, I'll just use m without a subscript, can be also thought of as doing the rise over the run. In Leibniz notation, we can write this derivative as dy dx, where the dy is the rise and the dx is the run. So in our picture, I can think of this delta x as the same thing as being just dx. This would be the run, and now dy, therefore, will be the rise. So the length of this green line segment we can call dy. This suggests that we can think of Leibniz notation for a derivative as a regular fraction of two different values called differentials. This is the differential of y, and this is the differential of x. And since the slope of the tangent line is the same thing as f prime of a, I can take this differential of x and multiply it to this side of our equation, giving me that dy is equal to f prime of a times dx. So when x changed from a to b, we see that the tangent line experienced a vertical change, which is not the same as the vertical change of the function itself, which would be this length. This length is the actual change in the function we'll call delta f of x, or just delta y for short. So for one delta x, or dx, because we have two functions in play here, there will be two different changes in y. The change experienced by the tangent line we will refer to as dy, or the differential of y, and the vertical change experienced by the function itself we'll call delta y. So if dx, or delta x, we'll use these symbols interchangeably, is small, in other words, we don't go too far away from the point of tangency, then we know that dy will be approximately the same size as delta y, where delta y is the actual change in f of x over the interval from a to a plus delta x. And dy is an approximation of delta y. In some cases, calculating delta y is either very complicated or impossible if the function is not known, but its slopes are known. So in cases where delta y is complicated, dy can offer us a simplified way to get an approximate answer. And in cases where delta y is impossible to know, dy can give us a chance to at least approximate the unknown delta y. Now the vertical gap between the two outputs can be thought of as an error in the approximation. We use capital E for that. And it should be easy to imagine that the smaller the value of delta x or dx, the smaller the error will be. We will see several examples of us applying this in the next few slides, but take note that given a derivative statement, dy dx is equal to f prime of x, then you can solve for dy and write dy equals f prime of x dx, and this is called the general differential of y. We say general because x is variable. You can pick different values for it. Okay, let's go to the next page. Consider the function y equals e to the negative x times cosine of 2x. Find the general differential of y. So we find y prime, and I'll use dy dx for that notation. Now this function is a product of two functions, so I have to use the product rule to differentiate it. We'll do the derivative of e to the negative x using chain rule will be negative e to the negative x times the second function cosine 2x plus the first function e to the negative x times the derivative of cosine 2x, which will be, using chain rule, negative 2 sine 2x. I'll do some factoring. We have some negatives we can factor out and exponentials, leaving cosine of 2x plus 2 sine 2x, and I'm going to multiply this differential dx to the other side. So we get dy, the general differential of y, is equal to this derivative times dx. This is our general differential. It's general because an x has not yet been chosen, which we'll do in the next step. Find the value of this differential specifically at x equals 0. So next we substitute 0 in for all the x's in this derivative, and we get negative e to the 0 times cosine of 0 plus 2 sine of 0 times dx. Sine of 0 is 0, so we're going to get 0 for this expression. Cosine of 0 is 1. E to the 0 is 1. So in the end, we get dy is equal to negative 1 times dx, or just negative dx. Now we'll find the value of this differential at 0, and then furthermore, where we substitute 0.4 in for the delta x, or the dx. That gives us that dy is equal to negative 0.4 in this case. Let's make sense so far of what we have here. Let's reproduce this image using Desmos. Type in the function using function notation. Let's zoom in to the area of interest. I'm going to create a dynamic, a movable tangent line. Create a slider, let little a equal some number such as 1. And then let's create bounds from negative 1 to 2 to match my current zoom level. The point of tangency will be at a, comma, f of a. Let's make it black and turn the drag feature off. Currently, you can just grab this point and move it if you want, but toggle that off and now I cannot. But I can still move this slider to move that point around. Let's park a at 0 and click on label. Now to make the tangent line, the equation is y minus the y coordinate, and the y coordinate is f of a, is equal to the slope, which is f prime of a, times parentheses x minus a. We'll make it orange. And now I have a movable point and tangent line. Animation mode, play forward only, slow down the pace of drawing and hit play, and you can see the tangent line changing as the point moves along the curve. But let's move a back to 0 so that we have the image that we're using in this problem. We're considering the location x equals 0, so the point of tangency is being drawn at this point, which coordinates are 0, 1. Now this 1 was revealed by the technology, but we can easily confirm. If I think of this function as f of x, then f of 0 would be, this would be e to the 0, which is 1, and this would be cosine of 0, which is also 1, confirming that we get 1 for the output. Now if you stay in this immediate area near x equals 0, then the tangent line and the function ought to behave pretty similarly to each other. The next thing we considered was a change in x of 0.4. So from the point of tangency, we go to the right, this dx, or delta x, of 0.4. So that takes me from an x coordinate of 0, which was my a value, to an x coordinate of 0.4. We also saw that from this calculation, the slope of the tangent line was negative 1, and performing this calculation to get negative 0.4 gives me a differential value dy. That's a change in output of the tangent line of negative 0.4. Now this orange line has slope negative 1, so you do expect that the run and the rise will be equal in magnitude, but opposite in sign. And lastly, we want to find delta y for this same value of dx or delta x. Well, in this drawing, that will be the vertical change experienced by the actual function. So whereas dy is this length, delta y will be the length shown here in this image. Well, this point on the function would have coordinates 0.4, comma f of 0.4. So delta y over the interval from 0 to 0.4 will be f of the right endpoint of this interval minus f of the left endpoint of this interval, giving us e to the negative 0.4 times the cosine of 2 times 0.4, which is 0.8, minus f of 0, which we already calculated was 1. Let's approximate what this is in decimal. In Desmos, I'll type in f of x equals e to the negative x times cosine of 2x. F of 0.4 is about 0.467, and then minus f of 0, or we could just say, since f of 0 is 1, and we get approximately negative 0.533, rounding to 3 decimal places. Now notice that the predicted change in y-coordinate of negative 0.4 is not too far off from the actual change in y-coordinate experienced by the function. So we have that dy is approximately the same value as delta y, or in other words, negative 0.4 is approximately negative 0.533. Now, this particular approximation isn't all that impressive. You can see from the image that we do expect a significantly large error value. Visually, you can see that in magnitude, dy is a little bit shorter than the magnitude of delta y. In other words, 0.4 is less than 0.533. The negatives indicate that the y values dropped as the x value increased. If I had chosen a dx that was smaller, you would expect the approximation to improve. In other words, the error to shrink. So if this had been my dx, keeping us close to the point of tangency, the gap between the tangent line and the function is much smaller. Also bear in mind that dx can be a negative value. In this example, dx was 0.4, suggesting we moved to the right. If dx had been negative, we simply would have repeated our analysis, but moving to the left from the point of tangency, and then comparing the output of the function and the output of the tangent line. Let's see how the mathematical ideas here can be useful. Let's go to the next page. Consider the function y equals the cube root of x. Find the general differential dy. Well, the cube root of x is x to the 1/3. So the derivative with respect to x will be 1/3 x to the negative 2/3. So dy will be equal to, this negative power moves the x to the denominator, and then the 2/3 power is the cube root of x squared. So you have 1/3 times the cube root of x squared, and then this dx will be multiplied to the right side, which I'll just put in the numerator of that fraction. And this is my general differential dy. Next, we're going to find the local linearization, capital L of x, of this function at x equals 8. So this picture we have over to the right, it is not to scale. It'll just serve as a tool to understand what's going on, but we have the cube root of x as some function, and we want to find the local linearization when x is 8. Well, this point of tangency would be therefore 8 comma f of 8. And of course, we can think of this function y as f of x and plug 8 into this function, and the cube root of 8 is just 2. So this point is 8 comma 2. Now 8 is a convenient choice to work with for this function because its cube root is a whole number. 7 would not be a convenient number to be working with here because the cube root of 7 is not as convenient. Next, we want to find the slope of this tangent line. Well, that'll simply be f prime of 8. Keep in mind that dy dx is just f prime of x. So we need to plug in 8 right here for this x. 1/3 8 to the negative 2/3. That's the same thing as 1/3 cube root of 8 squared in the denominator. The ordering of doing the square, you can square the 8 first and then do the cube root, or you can do the cube root and then square. That's actually easier to do if I'm not using technology. Cube root of 8 is 2, and then square that is 4, and then times 3. We get a slope of 1/12. We know the point it's passing through, 8, 2, so we can construct the equation of the tangent line. Using point slope form, we do y minus the y-coordinate, so y minus 2 is equal to the slope of 1/12 times x minus the x-coordinate, which is 8. That gives me y minus 2 is equal to 1/12 of x minus 8/12, which simplifies to 2/3. And now we're going to add 2 to both sides. And of course, adding 2 to negative 2/3, I would need a common denominator and change that to 6/3. So negative 2/3 plus 6/3 is positive 4/3. This is our local linearization, and we'll make it complete by changing y to L of x using function notation. This is the equation of our orange line in this image. Use L to find a fraction of integers that predicts the value of the cube root of 8.1. Now, the cube root of 8.1 is going to be an irrational number with decimals that go forever. But the local linearization will allow us to approximate this value with a fraction. Let's see what that looks like. First, decide how 8.1 compares to 8. How far over to the right from 8 do we go? And we increased 8 by 0.1. So our image here is not to scale. So let's say that this length here represents this dx of 0.1, taking us to x equals 8.1. So this point on the function would have x-coordinate 8.1 and y-coordinate cube root of 8.1. But instead of plugging 8.1 into the original function, we are going to plug 8.1 into this line instead to find L of 8.1. And we'll use that to approximate, trusting that our error will be small. Keep in mind, this image is not to scale. So L of 8.1 will be 1/12 of 8.1, and 8.1 is the same thing as 81/10, and then we're going to add to that 4/3. You can see why it will be possible to convert all of this to a fraction. Now, I'll use technology to speed this up. I'll type in L of x equals 1/12 of x plus 4/3, and now we'll plug in 8.1, and then use Desmos to convert to a fraction. This saves me a little bit of time, although we could have done this by hand. and we get 241 1/20ths. This is an approximate value of the cube root of 8.1. And we will now use technology to compare this approximation to the actual value of cube root of 8.1. Now keep in mind that the cube root of 8.1 is an irrational number, which means that in decimal form, the decimals would go forever without a repeating pattern. When I type in, I'll use virtual keyboard, functions, nth root, cube root of 8.1. Or you can also type in 8.1 raised to the 1/3 power. So the number that we're seeing here is actually a rounded number. I'll go ahead and show all the digits in my notes. 2.00829885025. If I stop the decimals there, then this is an approximation. I can use an equal sign if I suggest that the decimals would go forever. Now notice in Desmos, there is no option to convert this to a fraction. That is because this is an irrational number, meaning that there is no fraction of integers that this simplifies to, which is one reason why using the local linearization to approximate the cube root of 8.1 and getting 241 over 120 is so interesting. We get a fraction that approximates the value of an irrational number, or in other words, a number that cannot be written as a fraction. Let's just change this fraction back to a decimal form. And in decimal, we get 2.008 and then repeating 3. Put a little bar above that 3 means that 3 repeats. Now decimals that go forever but with a repeating pattern can be written as fractions, but irrational numbers have decimals that go forever but without a pattern, and they cannot be written as fractions. You can see just how similar the numbers are. In summary, we get that the cube root of 8.1 is approximately equal to the fraction 241 over 120, meaning that in reality, this gap right here is extremely small. Remember, the image in our notes is not to scale. Analyzing the situation with technology, I already have the tangent line. Let's type the original function, change colors of everything. I'll make 2 vertical lines, one at x equals 8, I'll make it red, and another one at x equals 8.1, I'll make it green. So at this scale, we can see 2 vertical lines very close to each other. Let's zoom into this area. The point of tangency is here at 8, 2. Notice that on this viewing window, the tangent line and the curve look indistinguishable from each other. I'm going to go to 8.1 and continue to zoom in here until I can see that they are different. So at this zoom level, the orange is the tangent line and the black is the original function. So on the black function, this output is a rounded version of the exact cube root of 8.1. But instead of using this number as the cube root of 8.1, we used this tangent line result, 2.0083, and then the 3 repeating, which is the value of this fraction, 241 1/20ths. Now this question did not ask for it, but here was my general differential dy. If I had substituted into it x equals 8 and dx equals 0.1, then I would have got the output 1 over 120, which would be a positive value and the length of this green segment from the red line up to the tangent line. In other words, if I had taken this y-coordinate and added to it this dy, then I can get the output of the tangent line. So another way to get this 241 1/20th would have been f of 8 plus that differential dy. And f of 8, of course, was 2, and that differential 1 over 120. So when I get a common denominator, I'd have 240 over 120 plus 1 over 120, which is why we're getting 241 over 120. This is an alternate way to arrive at this result. Find f of 8 and add to it the specific value for the differential dy after plugging in these values into dy. So you see on this page 2 different ways to arrive at this result. In summary, option 1, find the local linearization, then compute L of 8.1. This is the way we did it first. Option 2, find the differential at x equals 8 and when dx equals 0.1, then compute f of 8 plus that differential. Okay, let's go to the next page. The length of an icicle in feet t hours after 5 p.m. is given by the function y equals 0.5 square root of t plus 0.25. Find the local linearization L of t of this function at 2 a.m. Well, t measures the number of hours after 5 p.m. So when t is 0, that means we're at 5 p.m. A negative t value would be before 5 p.m. and a positive t value would be after 5 p.m. So on a t number line, if t equals 0 corresponds to 5 p.m., then what t value would I need to represent 2 a.m.? We'd have to count how many hours there are between 5 p.m. and then 2 a.m. And it's 7 hours to midnight and then 2 more hours. So this would mean that t would be 9 hours after 5 p.m. So this time right here tells us that we should be using the value of t equals 9. Okay, the local linearization is just the equation of the tangent line at that time. To help us with notation, let's call this y function f of t. So at 2 a.m., the length of the icicle is given by f of 9. Plug 9 in, so we have 0.5 times square root of 9 plus 0.25. Square root of 9 is 3, times 0.5 is 1.5, and add 0.25 to that, and we get 1.75. Now the interpretation of this number, it's the length of the icicle in feet. This is how long the icicle is at 2 a.m., in other words, when t is 9. Now let's find the derivative of this function. I'll change the 0.5 to a 1/2. The derivative of square root of t is 1 over 2 square roots of t, and then the derivative of the constant will be 0. So our derivative function is 1 over 4 square roots of t. Now let's find the slope of the tangent line by finding f prime of 9. So that's 1 over 4 times the square root of 9, which is 3, and we get 1/12 again. Now this is a rate of change. It's measured in feet per hour, and it's positive, suggesting that the icicle is growing at the instantaneous rate of 1/12 feet per hour, in other words, 1 inch per hour, at 2 a.m. We'll call this the instantaneous growth rate of the icicle at 2 a.m., in other words, when t is 9. So now we can construct the local linearization, or the equation of the tangent line. We're using t's as my independent variable, not x this time. So you have y minus the y-coordinate. That y-coordinate is this 1.75, is equal to the slope, which is this 1/12, times t minus, and then t-coordinate, where we're finding tangency, is when t is 9. I'll switch 1.75 back into a fraction. This is 7/4. Distribute the 1/12. 9/12 is 3/4. Now add 7/4 to that, and we get a positive 4/4, which is 1. So here's the equation of our tangent line, and now I will simply change the y to function notation, saying L of t. This is our local linearization. Now we will use this function to approximate the length of the icicle at 2:15 a.m. Well, to go from 2 a.m. to 2:15 a.m. means that we went from 9, t equals 9 hours, and then 15 minutes is a quarter of an hour. So this t value will be 9.25, suggesting that we have a delta t, or a dt, of 1/4, 0.25. But given our approach here, I don't even need to know delta t. All I have to do now is plug in 9.25 into my L function instead. 9.25 is 9 plus a quarter, and I could take the time to get a common denominator, but let's speed this up with technology and figure out what fraction this is. So this time my L of x, I'll still use x when graphing, even though on paper we're using t as the independent variable, but L of x would be 1/12 of x and then plus 1, and then we want to plug in 9.25 and then convert to fraction. And this is an approximation of the length of the icicle at 2:15 a.m., so this will be measured in feet. And then finally, use technology to compare our approximation to the value of the function at 2:15 a.m. So if I plug 9.25 into the function, I would get 0.5 times the square root of 9.25 plus 0.25. In technology, graph the function, make it black, output 2 vertical lines, one at x equals 9 in red and one at 9.25 in green. Now the point of tangency is where the red intersects the graph. And now let's zoom in around the green line until I can see a clear distinction between the tangent line and the original function. So this point right here represents the actual length of the icicle using this model when t is 9.25. If I want to see more digits, I type in f of 9.25. This would also be an irrational number, showing all the digits we have: 1.77, 0.69, 0.63, 257. The digits would continue, and our approximation, which is a fraction of integers, 85/48, with technology, convert this fraction back to decimal, and we get exactly 1.77083, and the 3 repeats forever. So this outcome here we'll refer to as the exact length of the icicle, and using a local linearization, this fraction 85/48 is an approximate length, and they are not far off from each other. And this concludes our lesson on local linearization and how it can be useful to help approximate complicated mathematical numbers.